Dublin, who is a professor in the School of Veterinary Medicine at UC Davis. She leads a translational research program that examines how environmental air pollution, particularly particulate matter, affects hemostasis and coagulation in humans and animal models of disease, as well as the role of these systems in mediating adverse cardiovascular effects. And with that, I'd like to turn the microphone over to our speakers. Dr. Bine will be starting this afternoon, and so welcome.
Thank you. I am mic'd up. Thank you for that introduction. Can everybody hear me okay? Yeah, good. All right, so the title of our talk, Health Effects of Central Valley Particulate Matter. The investigators are Tony Wexler, who is the PI. Unfortunately, he could not be here with us today. Keith Bine, that's me. I am talking in his stead. We have Dr. Laura Van Winkle, who also could not be with us today, and then Dr. Kent Pinkerton, who is sitting right here, Dr. Fern Tablin, and Dr. Dennis Wilson, who has since retired. So, obviously this work is sponsored by the California Air Resources Board. That's why we're here giving this talk. I want to start with an outline of what we're going to present today. And first, just give you a little bit of the background, kind of framing the project. Where's the motivation? What were the objectives? And then I'll talk about all the PM sample collection, the filter extractions, as well as the chemical analyses. Then I'm going to hand it over to Dr. Pinkerton. He'll do the animal exposure studies. And Dr. Tablin will do the platelet data. And then for the conclusions, it will be me and Dr. Pinkerton again. So let's start with the study motivation. So there was a 5-year health effects research center at UC Davis called the San Joaquin Valley Aerosol Health Effects Research Center, and they found a lot of different health effects associated with particulate matter in the San Joaquin Valley. And so several questions came out of that health research center. One of them are the responses due to urban or rural PM. What is the dose-response relationship? What are the time courses for these responses? And how do these time courses differ for pulmonary responses versus systemic responses? So that's the motivation for the study. And our objectives was the comparative PM toxicology and mechanisms of action. First of all, urban versus rural PM. We chose an urban site in downtown Sacramento, the ARB building cornered on T and 13th Street. And then for a rural site, we did UC Davis Center for Health and the Environment. For toxicological endpoints, we did pulmonary responses as well as systemic responses. For the dose response part of this, we did intratracheal installations. We used doses in the 10 to 100 microgram range and a 50 microliter delivery volume. And for the response time course part of this, we did 1, 2, and 4 days post-installation. And the bonus objective here, which was not originally a part of the project, was the comparative assessment of different PM filter extraction techniques. This is both compositional and toxicological. And the two techniques that we'll compare that I'll talk about are the multi-solvent extraction versus a spin-down extraction, acronymed MSE versus SDE. So those are the objectives of the study. And the study team, there's a lot of us, highly interdisciplinary. So for thrombosis, we have Fern Tablin, and for lung cell biology, we have Drs. Winkle and Pinkerton. And for chemistry and the aerosols is me, and Dr. Wexler is kind of in the middle of everything, and this is a classic Venn diagram. And so I come back to the outline just to highlight where we are now. So we're going to start with the PM sample collection, the filter extractions, and the chemical analyses. So first of all, we'll start with our sampling sites. First, our urban site is in downtown Sacramento, as I said. It's at the northeast corner of T Street and 13th Street. This is an ARB building. We are on the very top. It's a 2-story building. And in this area, the source mixture is high traffic. We have densely populated residential areas, commercial sectors, as well as industrial sectors. And there's a little red dot where the sampling site actually was right there. And for the rural sampling site, we chose the South Campus at UC Davis at the Center for Health and the Environment complex. It's on the southeast corner right here. We're surrounded by agricultural lands, so The sampling site was on top of a single-story building. It was a lab building, and the source mixture is obviously agricultural. There's some vehicular traffic, but it's low density, and the residential area is sparsely populated. So these should lead to two very different types of particle compositions. Next, the sampling equipment and the protocols. We used PM 2.5 high-volume samplers. These are Tisch environmental samplers. We used the PM 10 size selective head. They're operated at 40 cubic feet per minute. We collected a coarse fraction on aluminum foil substrates. These were pre-baked at 500 degrees Celsius for 24 hours to clean them. And then the fine fraction were collected on Teflon-coated glass microfiber filters. These are Paul Corporation MFAB TX40 filters. They were pre-cleaned via successive sonication and millicube water, dichloromethane, and hexane. For the sampling protocols, the field studies were conducted simultaneously at both sites. Both sites had several high-volume sampler systems. And we did two studies, one in the winter and one in the summer, both in 2011. I collected PM samples weekly for about a month, and then we stored them in our freezer until we did the filter extractions. So filter extraction techniques, what's the problem? The problem is we have to get the PM off of the filters, and this introduces all kinds of sources of potential bias. So there's several different filter extraction techniques that are available, not in the literature, but each lab has its own that they like to use. And different labs employ different techniques, potentially leading to bias when you intercompare studies and things like this. And the technique that you employ, it can have an effect on toxicological outcomes. So what do we do? How do we decide on which filter extraction technique we're going to use for this particular study? Well, this is where we kind of veer off course of what we proposed to do, and we designed a pilot study. And the first phase of the study is we selected 5 different filter extraction techniques. We used the one that the EPA uses, which is a simple sonication in water, followed by lyophilization to remove the water. Then you get a dry mass of PM, and then you go and you deliver that to the animals or the cell line. Multi-solvent extraction is the technique that I developed under different funding, and I've been using it in my lab for several years now. And then there's a spin-down extraction, which has been, was developed by people in Dennis Wilson's lab, and it's been used in their lab for several years as well. And then there were a couple others that were various hybrids of these. And so first thing we did is we pre-screened all 5 of these extraction techniques. We used in a quantitative PCR analysis on a THP1 monocyte cell line. We employed a 6-panel assay looking at IL-1 beta, IL-4, IL-8, GMS, CSF, CYP1A1, and COX-2. And we selected the top 2 techniques that elicited the most response relative to a filter blank extraction control. So the 2 techniques that came out on top were the multi-solvent, and part 2 of this pilot study was a detailed compositional and toxicological intercomparison of the extracted PM using these 2 techniques. And we used in vivo dose response studies. So we did 2 things in parallel. Not only are we comparing the 2 extraction techniques, but we're also doing the dose response at the same time. And then we going to choose the best technique based on these studies to do the time lag studies. So first, we'll detail the multi-solvent extraction. And again, we're doing only PM 2.5 here, so these are Teflon-coated borosilicate glass microfiber filters. This is a flow diagram. I can step you through it. The first process is we're going to sonicate the filter in water for a couple hours. We're going to remove the filter. We'll let it dry and reweigh it, and I'll get to this path later. But then we take the water sonicate, and we do a liquid-liquid extraction. We're trying to pull the organics out of the water phase, and we're going to use dichloromethane and hexane as our 2 organic solvents to pull this stuff out. And then once we do our liquid-to-liquid extractions, we're going to filter it using a millipore microporous membrane filter to get any potential microfibers that shed the filter during the sonication process out of the extract. And then we're doing the same thing here. We're going to remove the dichloromethane, remove the hexane, and these go to the final box here. And then we take the filter that's been dried and reweighed, and we're going to sonicate it again in dichloromethane. We're going to filter it. We're going to remove the dichloromethane and go to the final box. Then we take the filter out again, dry, reweigh, sonicate in hexane, filter, final box, and then reweigh, store the filter. And finally, we put everything back together. We remove all the solvents. We partition it into the number of aliquots that we need for chemical analysis and toxicological studies. And we do the final weights and we store it until the tox studies. So that's the multi-solvent extraction technique. The next one is the spin-down extraction. And again, this is PM 2.5, so these are the microfiber filters. Oh, that's the wrong one. So the first step is you remove the top layer of the filter membrane from the backing, and you roll the filter membranes up and you add it to the top of a Kaya shredder. So Kaya shredder is used in cellular biology as a cellular homogenization technique. It is essentially shredding higher molecular weight compounds into lower molecular weight to get a lower viscosity homogeneous lysate. And you weigh the top of the shredder column with the filter membranes in them to get your pre-weight. This is the extraction pre-weight. Then you add 500 microliters of PBS, and this is without the calcium chloride or magnesium chloride. Then you probe sonicate for 5 seconds. You attach the collection tubes to the centrifuge, and you centrifuge for 4 minutes at 7,600 Gs. The supernatant is collected from the tubes and is transferred back to the column. The membranes are sonicated again in the supernatant and then centrifuge again, and you repeat this process twice. Finally, you take the PM sample resuspended in supernatant and you filter it through a clean column, and then any supernatant lost during the process is replaced with fresh PBS to obtain a final volume of 500 microliters. It should be 500 microliters, not milliliters, I apologize. And then the extracted membranes in the original column, they're washed with distilled water. They're centrifuged. The extracted membranes in the column are dried in a speed back for 6 hours. Extracted membranes in column weighed to obtain the extraction post weight, and then you subtract the pre and post to get the extracted PM mass. So that's a lot of steps and a lot of information. So let me just kind of summarize the differences between these two techniques. They just have different objectives. For the multi-solvent extraction, I designed this for some source-oriented sampling studies that we did. I published this in Atmospheric Environment. And the objective was to maximize the extraction efficiency. I want to get as much of the PM off of the filter as possible. I want to minimize any compositional biases. I don't want to leave the organics on and bring all the water solubles off. I want to pull everything off the filter. And I want to try to minimize my extraction artifacts. These are the filter glass microfibers. They're unavoidably present in the extract because of the sonication process. They just come off of the filter. And so it was shown in this work that the selective filtration, this is a microporous membrane filtration, moves about 60 to 70% by mass of these glass microfibers from the extract. And the objective of the spin-down technique was solely to maximize the removal of these fiberglass microfibers, as well as to kind of avoid introducing any organic solvents into the process. So the key differences between the two techniques are, one, the solvents that are used. The multi-solvent uses water, dichloromethane, and hexane. The spin-down technique sonicates directly into the delivery vehicle, which is the PBS solution. And then for the post-extraction cleanup steps, the multi-solvent uses a microporous membrane filtration, whereas the spin-down uses a centrifugal homogenization and filtration. And then finally, for gravimetric analysis, for the multi-solvent, you're directly measuring dry PM mass, whereas for the spin-down, you're using the difference between pre- and post-extracted filter mass to obtain the extracted PM mass. So those are the differences between the techniques. And this shows you the breakdown between the different steps of the multi-solvent extraction, the fraction of total mass that is extracted during each step. So you see, most of the mass is extracted during the water extraction, right? Upwards of 80 to 90%, followed by the dichloromethane in red, and that's the extract. And the soluble refers to the liquid-liquid extraction of the original water extract. And the top bar, the DMCM, refers to sonication and DCM. So the first bar here is the urban sample. The second one is the rural sample, and the final one is the field blank. The things to note are the extraction efficiencies. For the urban, we removed about 95% of the PM mass that was collected on that filter. For the rural, about 97%. And then for the field blank, we extracted about almost a milligram, which represents about 2% of the total extracted PM mass. And so that's the breakdown of the multi-solvent technique. This is not possible for the spin-down technique because it uses the difference between filter weights, which couldn't be done. So for the chemical characterization, so what's new here? First of all, the sample preparation techniques. How do we prepare the PM for subsequent chemical analysis? So the goal here is to do all the chemical analysis on the extracted PM sample. This is not how it's typically done. Typically, instruments are run in parallel to measure different attributes of the particle population, or they may be collected on separate filters and different filter media for different kinds of chemical analysis. So that's new here. We're performing an exhaustive chemical characterization on a single PM extract, so we have to do some new sample preparation techniques. And then also we're analyzing the same PM and field blank extracts that are used in the subsequent exposure studies, and like I just said, this is typically not what's done in most studies. And then we're doing a comprehensive compositional and a comparison of these two techniques, and this has never been done before. So what are the components we're going to analyze? Trace metals using inductively coupled plasma mass spectrometry. These are the elements that are analyzed. I just lost my pointer. There it is. From lithium out to uranium. And for sample preparation, we do a liquid-liquid extraction and dichloromethane and hexane. This is to remove any of the organic layers that may encapsulate the metal core particle. And then we'll do an acid digestion and nitric acid followed by a sonication, a dilution, and then the samples are ready for analysis. For water-soluble inorganic and organic ions, we use an ion chromatography, automated colorimetry, atomic absorption spectrophotometry. We do the standard water-soluble inorganic ions as well as 17 organic sugars and 9 organic acids. And a pretty straightforward sample preparation is just dilution, sonication, and then a pre-filtration step to remove the particles from the dissolved salts. So next is molecular organic compounds, and this was done by the Desert Research Institute, and they used thermal absorption gas chromatography mass spectrometry. They analyzed 38 different PAHs, 47 high molecular weight alkanes, alkenes, 18 hopanes, and 12 steranes. And so this is where we have to get a little bit tricky with our sample preparation. They're designed to analyze off of quartz filters, and we have extracted PM. So we have to redeposit our extracted PM back onto a tissue quartz filter. So how do we do this? First, we take our extracted PM and we sonicate it in methanol, and then we use a very slow methanol drip onto a tissue quartz filter with a reverse nitrogen flow. It puts back pressure on the back of the filter so it doesn't drip through, and it also helps speed up the evaporation of the methanol. And so I know the exact weights of everything that's been extracted, so I can compare the mass of what's been extracted to the pre and post weights of the tissue quartz filters after this process, and I can determine what is the mass transfer efficiency. And if we do that calculation over all the samples, you get about 97 plus or minus 8%, which is within the error of the analysis itself. So we did a good job there. And then ECOC is done by thermal optical reflectance. DRI did this analysis for us as well, and they used the same tissue quartz filters, so I did the same analysis and the same sample preparation for this. And finally, for corrections and error estimates, all the PM composition data is field blank corrected as well as process blank. There's a process blank that's included in every single step. And the measured errors are propagated to obtain the 99% confidence intervals. So that's how we did the chemical characterization. And so we'll start looking at some of the data. And all this original data will be mass fraction data. So that's the mass of the particular component relative to the total mass of extracted PM. There are two comparisons here. There's an urban. We're comparing the spin down to multi-solvent as well as the rural, the spin down to multi-solvent. So the first two bars, these are the urban. The first bar is the multi-solvent. The second bar is the spin down. And these next two bars, the blue and orange, are for the rural. And the first bar is the multi-solvent. Second bar is the spin down. These are the major metals that were detected. And you can see in general that the multi-solvent has a higher mass fraction for almost every single element measured, both in the urban as well as the rural sample. This is the sum of all the trace, which I show on the next slide. Here are all the trace metals that were detected. Again, we have the urban multi-solvent versus spin down and the rural multi-solvent versus spin down. Again, you see in general that the multi-solvent has a higher mass fraction for almost every single element analyzed for both the rural and the urban samples. So here's the water-soluble inorganic ions. Same structure. We have urban, are the first two bars, rural are the second two bars. This is mass fraction data. The green is the multi-solvent, the red is the spin down, blue is multi-solvent again, orange is spin down. Again, we're seeing the same trend here, is that the multi-solvent technique is consistently giving a higher mass fraction for each of the compounds analyzed relative to the spin down technique. Now we're looking at major PAHs. Again, the same structure here, urban and rural. The multi-solvent, this is the spin down. And these are the major PAHs that were detected. There's a lot of them here. I won't go through all of them. But again, you're seeing the same general trend, is that the multi-solvent technique has a higher mass fraction for almost all the individual components analyzed for relative to the spin down technique. And the totals are listed here. So those are the major pHs. For the minor pHs, it gets a little bit noisier. Again, we have urban and rural, spin down, and multi-solvent. And there are a few instances where the actual spin down is giving a larger mass fraction than the multi-solvent, but the general trend still agrees with all the previous slides, in that the multi-solvent is giving higher mass fraction relative to the spin down for almost all the components analyzed. And then we can look at the same thing for major non-aromatic compounds. These are high molecular weight, alkenes, alkanes, and again, urban, rural, multi-solvent versus spin down. Again, the same trend. The multi-solvent, here's the totals, is consistently higher than the spin down. And then here's for the minor molecular organic. Again, there's a lot of data here, but just showing the general trend that the multi-solvent consistently is removing a larger fraction of the organics than the spin down. And so finally is ECOC data. Pyrolyzed organic, total organic matter, used a conversion factor of 1.6, elemental carbon, and then the total OM plus EC. Again, we're doing urban, the first two bars, rural, second two bars. Green is the multi-solvent, red is the spin down, blue again is multi-solvent, orange is the spin down. Again, we're seeing total carbon, organic matter, everything is higher in the multi-solvent than the spin down. So the question is, why all these discrepancies? What's going on? So to look at that, we do a mass closure study. We're simply adding up all the chemical compounds to get the total mass closure. Here's the urban multi-solvent. Here's the urban spin down, rural multi-solvent, rural spin down. So total mass closure, the multi-solvent's up in the 90s, 92, 95. The spin down is down in the 50s, 60, 48. Where's all the mass gone? That's the big question. So we'll try to devise a way to figure this out. And so what we did was this kind of retrospective mass reconciliation thing. So from the mass closure data, we see that there's a large fraction of the extracted mass from the spin down technique that's not accounted for. For the urban data, it's about 36 plus or minus 7%. For the rural, it's about 52%. From the multi-solvent extracts, we see that they're well characterized by all the chemical components that we analyze, so we're not missing chemical components somewhere. The problem is that the spin down never directly measures the total extracted mass, whereas the multi-solvent directly measures this mass. The hypothesis is that this unaccounted PM mass is lost somewhere in the STE's process. So what do we do to try to test this hypothesis? So The primary issue is that the spin down extracts directly into PBS solution. And the PBS solution has very high salt concentrations. For example, there's about 5.3 milligrams of buffering salt in a 500 microliter volume compared to about 4 or 5 milligrams of PM that's being extracted. So there's a high probability of error, measurement errors in both the gravimetric. So how did I do? I wanted to compare the filter blank extract mass to this volume calculated PBS mass based on the volume. So I could use the volume calculated mass to correct for the extract mass and propagate the errors to quantify the uncertainties. So how did I do it? The methods. I took an archived aliquot of a filter blank extract and PM extract, and I apportioned them evenly among 6 new aliquots. And I blew down the methanol and any residual PBS water content under nitrogen atmosphere. And then I directly weighed the extracts via an analytical microbalance and calculated the average plus or minus a 99% confidence interval. The results, the percent difference between the weighted filter extracts and the volume calculated values was a 0 plus or minus 6%. So if we take the PBS adjusted PM extract masses, show a significant amount of mass lost, and for the urban was 44 plus or minus 9%, and for the rural was about 52 plus or minus 8%. So if we adjust the masses, we significantly improve the mass closure. We go from urban, which was 64%, up to about 110 plus or minus 13. The rural goes from about 48 up to 100. So this last slide is looking at the adjusted masses for the SDE to the MSE technique, and these are the enrichment factors. So a value of 1 means that the component was lost in equal proportion to the total mass loss. A value above 1 means that that component was enriched in the spin down relative to the multi-solvent. A value less than 1 means that it was depleted in the spin down relative to the multi-solvent. So we see a lot of variation here, but the metals, the PAHs, and the molecular organics were all depleted, whereas elemental carbon was highly enriched, and organic carbon was also enriched for the urban, but depleted for the rural, and the ions were heavily depleted for the urban, and about equal proportion loss for the rural. And so that concludes the PM sampling as well as the filter extraction and chemical analysis part. And so I'm going to hand it over to Dr. Pinkerton to discuss the animal exposure studies.
Okay, thank you, Keith. It really is a pleasure for us to be here today. We're really happy to be able to talk about the findings of this study that was supported by the Air Resources Board. As the outline shows, I'll be talking about the animal exposure studies. And we'll talk a little bit about the methods that we used for exposing the animals, how we did the toxicological assays that we implemented to try to understand what the potential effects would be for these PM samples. We also did a dose response. That was really critical for us because we really didn't know how much of a dose would we need to give that would actually elicit a response, and would that dose be somewhat similar to what could be environmentally relevant. But it was also important for us to actually do a time response. So actually, because we know through epidemiological studies that there can be a time lag that is associated with health effects that are associated with exposure to particulate matter. So in doing this study, let's see. As Keith has mentioned, that we really wanted to do some blind studies prior to even knowing what was the composition of the particles that, in terms of their chemical composition, to just give us a baseline level. And those studies were done to, again, look at the dose that we should deliver to the animals. And as mentioned, we did the dose response study. So this is just to try to give a little bit more complete detail about how the dose response studies were done. So we wanted to use a filter blank because that is very critical for us to understand, is there something about the filter that we're using when we collect particles that may actually have some sort of biological effect, and then do some comparisons between the two different extraction methods that are used. And Keith has gone into detail to talk about them. MSE is simply just using the multi-solvent extraction method, whereas SDE is the spin-down method. It's really just using water, pretty much, or a saline solution to be able to try to extract the particles from the filter. And again, we wanted to compare those two methods to try to understand, does one method give us a different result than the other? And as Dr. Bine has really pointed out, we get very different chemical compositions and through those two extraction methods. And so again, doing that, then we could go ahead and look at both extraction techniques and do the dose response study and then see exactly what was going on. And for us, it was really important because Sacramento, Davis were in that urban-rural interface. And so we felt as though the work that we could do here in Sacramento would really be a nice reflection of an urban location to understand what kind of particulate matter is present in an urban setting in contrast to a more rural setting. Now, some may argue that Davis is not that rural, but where I live at the Center for Health and the Environment, we're in the middle of agriculture. So we're located a mile south of the main campus for Davis, and we have agriculture surrounding us. And we really felt that that would represent something uniquely different, and I think in reality that did prove to be the case. And again, the second part of this is the time delay study or the time lag study to really kind of try to characterize this, because as toxicologists, we typically have one shot at looking at what may be toxic. And it was very nice because as we worked with the Air Resources Board, and in particular with Dr. Dreschler, we really came to a point where we said, let's look at different time points to see if if we've really hit where is the most important time to be looking at biological effects following acute exposure, a single exposure to particulate matter. As toxicologists, I don't know why it is in our psyche, but we always think it's 24 hours post-exposure, that is the key time to look at. So we chose that as our first time point, 24 hours, and then we also chose 2 days and 4 days as a post-lag time point. So in looking at that, let me go ahead and talk a little bit more about this. So Keith has told you that all of the particulate matter and the filter blank extracts that we used actually is suspended in physiological buffered saline. We wanted this to be absolutely what would be the word? Innocuous as much as possible when you're putting a liquid down into the lungs of a mouse. Now, Keith had mentioned that we actually were doing intratracheal instillation, and we actually decided we wanted to try to improve that technique. And so we thought if the mice, if they're put down at a certain level of anesthesia, that they would have a response, that we could actually do an aspiration technique. So we actually have a number of graduate students who've been involved in these studies who've actually learned to do oral pharyngeal aspiration. They simply use an Eppendorf pipette tip, and they put in a known volume of the suspension, and then in essence with the mice, which we used mice, these are all valve C mice, we put them down to a level of anesthesia that they wouldn't react to us, and we could basically just going in an oral manner, we could basically take the tongue, hold it, push it to the side, and you can easily slip the tip of the Eppendorf pipette tip right above the glottis, or basically right there at the epiglottis, so that in essence, when the mice is breathing, and actually they're breathing very quickly, but in essence, we can actually introduce that drop, basically the 50 microliters, which we decided to use, and they would actually spontaneously aspirate the material. We really felt if we did that, we would have a little bit more of a homogeneous distribution of the particles in suspension into the lungs, rather than by an intratracheal installation, which actually introduces a bolus of fluid into the lungs, and you're never quite sure exactly where that might go. So, but it's important that once we have these extracts that are in suspension, we want to make absolutely sure that we don't have them agglomerating. And that's exactly what a particle will do. Oftentimes, even the really tiniest of particles will obey the laws of gravity, and they will basically sediment. They'll deposit. And so the sondication was an approach that we used to make sure that we could create as homogeneous of a suspension of the particulate matter as possible. Now, we did this in such a way, though, too, that we didn't want to actually have the banging around of these particles to begin to induce basically a reactive kind of particulate. And so once we did that, then, as I mentioned, we used oral pharyngeal aspiration as our technique. We're using BALB-C mice. In this particular instance, we used male. Now, we know better now, but I guess we're supposed to use both male and female, but that would double our budget that we would need to do that. So we opted for the traditional male approach to this research. But we wanted to make sure that these mice, before we actually got them in, that they'd be acclimated. And so we maintained these animals in our facility for at least 1 week before we actually began the procedure. Everything that we did was under the institutional animal care and use protocol that was approved by the IACUC committee at UC Davis. So, and as you see here, our control mice and our treated mice, we were giving them 50 microliter suspensions. Now, you might say, what is that? And typically, for the multi-solvent extraction method, that was 50 micrograms in 50 microliters of the particulate. And as Keith has explained, in terms of the spin-down method, we actually realized that even though we thought we were going to deliver that, we actually delivered a lower dose. And that will be an interesting observation as we go along. But 6 mice were always used at each time point so that we could end at each exposure dose with the idea in mind that that would give us statistical power to see what is going on. Of course, as you know, more is always better, but we felt as though that this would be a reasonable sample size for the power that we were trying to work with. And so, in essence, after we did this, as I mentioned, there were times, and typically we were just waiting 1 day post-aspiration to do this work. So, okay, so the assay methods, sorry this is so wordy, but in essence, the big points are what are critical. One of the ways in which we can look at the biological response is to lavage the lungs of these mice with sterile saline, with the idea in mind that we'll recover cells that are present within the air spaces of the lung and also in the airways, and be able to count total numbers, look at their viability, and also be able to look at the differential of what is it that we're recovering from the lungs. And this is a typical approach to take for looking at changes that might be a reflection of injury and inflammation to the lung. The other part of that is that when you basically instill, this saline down into the lungs, then you pull back. In essence, we do that one in and one out. And when we spin down the cells, then we have the supernatant. And from that supernatant, we can measure protein. And the level of protein that is present within the supernatant can be a reflection of increased permeability of cells if we have some injury going on. So protein levels would go up in such a way. Dr. Van Winkle helped us with all of our quantitative RT-PCR, as well as Dr. Wilson, in looking at things that were going on. And so Laura has actually developed a method that actually, if you're ever a graduate student at UC Davis and you were in the Charlie Plopper era, you learned how to do airway microdissections. And so that was a technique that Laura implemented on here so she could look specifically at what's happening in the airways and then what is happening in the gas exchange region or the lung parenchyma. And because we had tissues in doing this, we actually were able to also fix tissues and do immunohistochemistry to look at what was going on in terms of some of the things we were trying to measure, but some of them actually have to do with the cytochrome P450 monooxygenase system that we thought would really be important because we thought, okay, Sacramento, they've got a lot of PAHs, Davis, maybe not so many, and we wanted to look at that. Dr. Wilson performed all of the histological evaluations for these studies. He is a board certified veterinary pathologist and has many, many years of experience in looking at lungs as well as many other organ systems. And he was really instrumental in helping us to understand what was going on in these single acute aspirations of particles and what was happening over time and based on dose. And again, Dr. Tablin will talk a lot more about the platelet. We'll do a little bit of tandem discussion here as we go through that. And again, the bioplex was to help us to look at cytokines. And again, that was kind of maybe a shotgun approach. Does cytokines tell us what's going on in terms of inflammation? And I think we kind of get mixed messages with looking at a whole variety of cytokines, but we'll talk a little bit about that. And then the statistics were done under the direction of some biostatisticians at Davis that we've really enjoyed working with. So these are some of the results, and hopefully you can kind of see that. If not, hopefully the handout, that's even smaller than what we see up here. But if we're looking at this, the best way to look at this is, again, this is the dose response, and so we're going to compare our solvent extraction technique to our spin down water technique. And so on the, let's see if I get my directions right. So left side is your spin down technique. Those are the light bars. And on the right side is am I looking? Okay, okay. And then on the left side, no, got that right? Left? Okay, all right. Well, light bars, extraction. Dark bars are the spin down method. And if you look at this, this is actually looking at a dose response curve. Now I know it's a little bit too large, too small to see, but remember the spin down technique, when we really came down to it, it was only about half the dose that we were giving with using the multi-solvent extraction method. But as you can see that actually we have a pretty robust response as the dose becomes higher. So in looking at that, that's what we're actually looking at, is that higher dose, as one would expect, would give us the highest number of cells. That's in the top panel that you're looking at. For the extraction method, we basically kind of saw a similar pattern, maybe to about the same degree. If you look at the middle panel, this is for neutrophils. And again, neutrophils are really a nice marker, a nice indication that we have an acute inflammatory response. That's typically associated with anything that if it causes immediate injury or damage, you're going to get an influx of neutrophils from the circulation into the air spaces of the lungs, and you'll actually recover them by lavage. And if you look, we actually seem to have about the same kind of response in terms of a neutrophil influx in that process. But again, remember, the spin down method has much less in terms of particulate compared to the multi-solvent, which has basically all of the chemical components that we would see within the air that we were collecting on those filters. And then the bottom panel is actually looking at the protein. Okay, so that's protein. And so again here, we're seeing some effects, but in general, typically the highest concentration, at least for the solvent extraction, which is on your right, is at the highest dose and the highest level. But again, these were concentrations that weren't producing a lot of permeability or injury to the cells. Now, Dr. Wilson looked histologically at both methods. So the top panel is showing the spin down, the bottom panel is showing the solvent. And although looking at this might seem a little bit strange, every one of these are showing a terminal bronchiole opening up onto an alveolar duct. So, and we start basically at low, medium, and high. These are just the doses. Again, we're not really showing the control, but the low is pretty much like a control. And if you look especially at the spin down method compared to the corresponding solvent method, it looks a little bit thicker. There's perhaps a little bit more cellularity that you're seeing in the tissues there. And that was a striking finding. And actually, Dr. Wilson took that approach, and so he looked at mean inflammation and lesion scores. So the top panel, number A, that's the lesion score. And again, looking at this on the left, we have the spin down, and on the right, we have the solvent. And there's a whole lot more, as we saw in that previous panel, for inflammation with that spin down extract. The lower panel is actually looking at inflammation scores, and it might be a little bit tricky, but we actually divided it into 3 parts, as you'll see that bar. The bottom part are the airways, the bronchioles. The middle zone is the parenchyma or gas exchange, and the top part is the vasculature. And again, this, as it says here, is an inflammation score. And what Dr. Wilson was doing, he was just looking in each of these regions and looking for the number of inflammatory cells that were there. And clearly, there's no question that it would appear for all 3 of those compartments, the spin down method for gathering the PM shows a much higher number of inflammatory cells in each of those 3 regions compared to the solvent extraction method. And so the next step was, okay, we want to look at a couple of things, and 2 of these are part of the cytochrome P450 monooxygenase system. So we looked at for cytochrome P450 1A1 and cytochrome P450 1B1. And so 1A1 is the top panel, 1B1 is the middle panels, and then IL-1 beta, I'm sure many of you know what that is. It's basically a cytokine that is involved in acute inflammation. So IL-1 beta is always usually a hallmark. If you have any kind of inflammation and there's going to be some recruitment going on, you're going to have an elevation in that cytokine. And this is actually something that was looked at in the conducting airways. And so this is work that as we look at it, again, we're kind of seeing a mixed response, but for example, if you look at the middle panel for the the cytochrome P450 1B1, we actually have a lot more activation than we see for the solvent extraction method. And that actually, frankly surprised us, because we figured the solvent method was going to capture all those PAHs much better than water extraction, because PAHs aren't able to remain, and they can be lost in the water extraction. And so, even looking at the bottom panel, which is our cytokine, our IL-1 beta, again, we do see that there is tends to be a greater effect in the spin down method compared to the solvent extraction method. Any questions about that? And again, it's clearly dose response. The higher the dose, the more you see. Okay. So Dr. Van Winkle did the immunohistochemical localization for looking at the cytochrome P450s. And these are shown here. Again, they're not going to really be that easy to see, and even on your handouts. But in essence, when we're looking at this, when you look for cytochrome P451A1, what you're looking for is probably expression either in an airway epithelial cell, or it's going to be in a macrophage, or it's going to be in a type 2 cell in the gas exchange. Dr. Van Winkle really was looking at the airways because that was where we really wanted to look at that. And in essence, I think you'll have to believe me on this, but in reality, this is actually shows some elevation, and I think she might have shown, well, no, I was going to say she might have shown a quantitative approach. So I wanted to take, because this is towards the end of the dose response study, I wanted to ask Dr. Tablin to talk a little bit about what's happening with platelets, because all we've been talking about is a lot of lung right now.
Thank you, Kent. So many of you know that platelets are a very important component of coagulation. So if you cut yourself, the cells that prevent you from bleeding are your platelets. But what you may not know is that platelets have become a very important component of inflammatory cells in the lung. And I need to give you a very short little primer about platelets so that you can understand what these P-selectin, LAMP1, and CD41 are. So CD41 is an integrin. It's an integral membrane protein. It's constitutively expressed on the platelet surface, so it's there all the time. And normally you would expect to see it in very high numbers. You're looking here on the left at the spin results, and on the right, the results from the solvent. And these are platelets that we call resting platelets that have not been stimulated. The study is done by taking whole blood and evaluating platelets specifically and looking for the expression of these markers. If the cells are not activated, you should see between 85 to 100% of the cells expressing CD41 on their surface. And the numbers here for the spin are within normal limits. What you will also notice is that the numbers from the solvent, including the filter, are way lower than for the spin. And the implication of this is that the platelets have been activated by something in the solvent. When platelets are activated, the CD41 that's on the surface can actually be internalized, it's recycled, but it also can be shed into platelet microvesicles, which are part of a procoagulant environment that might stimulate a clot, for instance, in the small microvascular capillaries in the lung. When we treat platelets with physiologic agonists, and that is thrombin, in this case, thrombin is a serine protease. It's an extremely potent physiologic agonist, and treatment of platelets with physiologic agonists results in the secretion of platelet alpha, dense, and lysosomal granules, and these are clear markers of platelet activation. And we can evaluate the release of those granules by looking at these membrane proteins from the granules that become expressed on the surface when the platelet is activated. So in panel A, you're looking at platelets that have been treated with thrombin, so they've been deliberately activated, and you're looking at the number of platelets in the population. We study 50,000 platelets per sample that are now expressing the alpha-granule membrane protein P-selectin. And you can see that the spin allows the platelets to be extremely responsive to thrombin. It potentially could make them even more responsive to thrombin. But interestingly enough, the solvent tends, in most doses, to inhibit activation. And the question might be why, and I'll get to that in just a minute. We can also evaluate lysosomal membrane protein 1, LAMP1, on the platelet surface. This is a lysosomal granule membrane protein, another indicator of platelet activation. And you can see here that the spin samples, the SDE samples, are very, very responsive. And again, the solvent samples are much less responsive. So why would this be happening? Why would we anticipate seeing such a difference? Well, if the solvent method does indeed activate the platelets, it may be that they are unable to respond to thrombin by adequately putting out a number of granules, or it is possible that there is some other effect of the solvent extraction that is toxic to the platelets. So I'm going to turn this back over to Kent, and we're going to turn our attention to the time delay studies now.
How are we doing on time? Fine? Okay. All right. So the time delay or time lag studies are really quite fascinating. Again, if any of you are epidemiologists, you're very well aware that we really have to look at this time lag to try to figure out what is the potential effect of any air pollutant, but especially particulate matter. So as I mentioned, we opted to do a time lag that would consist of times that would be 1 day, 2 days, and 4 days post-aspiration of the particulates. For this particular method, we used the spin-down method because, again, with a dose response, we were seeing the greatest effects there, so we opted to do just the spin-down method for this. But we chose, again, a rural location, i.e. Davis, South Davis, and Sacramento as our urban area. So in looking at this, the first panel that's shown here is the cells recovered by bronchoalveolar lavage. And what is shown here are the controls first, and then the Davis site, and then the Sacramento site. And what was quite interesting is that all of those cell numbers were actually down compared to control. However, if we took it a little bit further and looked for neutrophils as our indicator of an acute inflammatory response, you can see that definitely, even though numbers were down overall for total cells recovered by the lavage, we actually saw a significant increase in the number of neutrophils compared to control for both Davis and Sacramento. But if you look at Davis, the rural area, it was very acute. It was just the first day, and then literally the very next day on day 2, we were down at control levels. In contrast, if you look at Sacramento, we had an elevation that was significant after 1 day and after 2 days post-aspiration of that material. But by 4 days, we're back down to control level. So that was the first thing that we noticed as a distinct difference between our rural and our urban areas. So again, Dr. Wilson looked at the histological changes at the level of the terminal bronchiole and the junctions. So this is, in essence, going from the transition of a conducting airway into the gas exchange region. And he looked at these and did, so the top panels you're actually seeing these areas, again, kind of trying to show here's the terminal bronchiole, probably on the right side you actually see the terminal bronchiole at the bottom, and then as you go up towards the upper part, that's the alveolar gas exchange region. So in looking at that, he was again looking at these, and in this particular instance, he was looking at inflammatory cells. So that panel A is looking just at the neutrophils, our acute inflammatory cells. And it is interesting that although an asterisk was the only thing that said it's statistically significant from control, if we looked at that, it was just the Sacramento at the 2-day time lag that he had a significant elevation in neutrophils that were present in this bronchial alveolar duct junction. The middle panel is again looking at platelets. Dr. Wilson, he may be retired, but he has a great set of eyes. Did you do them? Oh, he immunostained. Oh, well, then I won't give him so much credit. so, so immunostaining, clearly, it was interesting to see this because you're seeing here that there is an elevation above control within this region. And again, do you know if these platelets were in the lumen or were they coming outside of the vasculature? Okay. But the immunostaining, at least, and you know, platelets are so much smaller than red blood cells. So, you know, it's really looking quite seriously about this. But what is really interesting is if you look at the Davis and the Sacramento, they both have what appear to be elevations, but we only have an asterisk over the Sacramento this is the 4-day time lag. So here we have something that's even more becoming apparent, becoming significantly different from the sham controls after 4 days. So clearly, you know, there is a lag in what is happening at this point. But this is localized to the lungs, these platelets. And then that third panel, C, this is basically PM density. And when I first looked at this I will give Dr. Wilson credit for. He was literally visualizing particulate matter within the lung tissues, which I find absolutely amazing. Since I work with a lot of tobacco smoke research, I have a hard time finding the tar even after heavy doses of tobacco smoke. So this was quite remarkable. But it is interesting. Look at Davis and look at Sacramento. So he's seeing particles at all of these time points. But it is actually interesting that as he goes with a larger time lag from actually the initial exposure, he's actually seen an increase in this index for the number or the density of particulate matter within the bronchial alveolar duct region, which would suggest that either particles might be being swept into this region, or this may be a place where they're actually being retained. Because there is a lot of concern that if we talk about the fact that if particulate matter actually is involved in sensitization or in exacerbating a respiratory condition, whether it is chronic obstructive pulmonary disease or it's asthma, this is the region where we would see the greatest effects. But again, it's an observation. These mice did not have asthma, and they didn't have COPD. And then in terms of the overall lung inflammation scores, again, this is just showing that there is a significant effect in Davis, clearly above control for up to 2 days time lag, but it's coming back down to control levels by day 4, whereas if you look at Sacramento, it's a little bit variable, but you literally have a greater inflammatory lesion score all the way out to 4 days post-lag time. Again, suggesting that maybe as toxicologists, you know, our rush to say 24 hours post-exposure is the time we should be looking at may be a mistake. And then again, this was looking at gene expression. I won't go into the details of this, but as you can see, there's a lot of things there. Probably, if you can read the very bottom part of this, the first column is basically key genes involved in inflammatory cell recruitment to the lung tissues. And again, if we're looking at that, it looks like we kind of get a mixed message, but again, sometimes it's Davis, sometimes it's Sacramento, but it's always in the day 1 time lag. And again, this might make sense because that's where gene expression will be elevated. Now, the middle column is conducting airway expression of key antioxidant and phase 2 metabolism genes. Again, this is a favorite area for Dr. Van Winkle, just simply because she's very much interested in airway epithelium and metabolic capability. And again, we're kind of seeing the same sort of thing. Again, I guess it just depends upon the gene you're looking at. Not all genes behave in exactly the same way in terms of their elevation. But it is important to keep in mind that the numeric designation on the y-axis is a fold change relative to control. So, for example, for this, well, whatever hemox is, I don't know what it is. Does anyone know? Is it? Okay. So in essence, you have almost a threefold increase for that gene expression, the mRNA levels, at the 1-day time lag. But it's going back down to control levels immediately. And then the third column is the parenchymal, or gas exchange expression for, again, the same thing, key antioxidants and phase 2 metabolic genes. And in essence, it looks as though typically if you're going to have an effect, it may be in that first day post-aspiration that's there. I don't know really what to say about the very bottom panel where we see Sacramento has a very significant, almost greater than a 4-fold increase in GCLM. Does anyone know what GCLM is? I should know, I'm sorry. Granulocyte cell something? Okay. But it is part of your phase 2 metabolism genes or your antioxidants. So, okay. So again, these are the sorts of things. And then here, Laura went back and she wanted to look at this cytochrome P450 system. And in looking at this, again, it appears as though, you have an effect that may not really be different. I don't know what to say. Your conducting airways are on the top. Your parenchyma or gas exchange is on the bottom panels. And in essence, it looks as though if we just take the parenchyma, for example, that we actually have a significant elevation in cytochrome P450-1A1 at the 4-day time lag. For Sacramento, you see it's significantly elevated at the 2-day time lag. So again, but if you look at the airways, it doesn't look like there's much that's going on there. So, but again, these are really fascinating things that we really want to try to understand. This is the multiplex cytokine assay that was performed by Dr. Wilson. And again, this work, Fern, are you going to talk about this? Oh, okay. So this is basically trying to just say, okay, in looking at this, we're just trying to figure out with this particular study, the serum would basically be your circulating cytokines in the blood, and that would be on this left side, and on the right side are the lung cytokines. And all I can say is that they kind of go up, but there's really, and it looks like, for example, lung eotaxin, that is one thing that we're always interested in looking at, that it looks like for both the Sacramento and the Davis at the 4-day time lag, you have a significant elevation in those cytokine, the lung eotaxin at that particular time when we're looking at this. So again, suggesting that there are many things that we could be looking at. Sometimes we frustrate ourselves by basically saying, we think we're going to find an answer, and we actually come up with more questions than we have answers. So now I'll turn it over to Dr. Taplin.
Thank you, Dr. Pinkerton. So the platelet data from the time delay study was very interesting because at 24 hours and 48 hours, there were no differences between the control exposure, the Davis exposure, or the Sacramento exposure. It was all the same, and we were very surprised. But as we thought back about some of the other data, and as we spoke, Dennis and I spoke about his finding the platelets in the lung at a late stage, some of this data became a little bit clearer. So we looked again at CD41B, that constitutively expressed integrin, at p-selectin, which showed no difference, and at LAMP1. And we looked again in resting and thrombin-treated platelets. Interestingly enough, the controls had higher expression, so mean fluorescence intensity reflects the number of molecules that bind the antibody. It's a good readout for how many actual integrins are on the surface, and there are 80,000 copies of this integrin on any single little tiny platelet surface. And it's very high, as it should be, in the controls, and it is lower, although not statistically lower, in both the Sacramento and the Davis samples. When we treat the platelets with thrombin and we look at the expression of CD41B, there is a large shedding of the CD140B or a recycling, we can't tell which, off the platelet surface, especially so from the Sacramento samples, but also there is a decrease not statistically significant from the Davis samples. So it looks very similar to what Dr. Wilson was finding in the lung. And interestingly enough, when we looked at LAMP1 and P-selectin, there was no change in P-selectin, either in the resting samples or the thrombin samples. They were all very consistent across the different exposures. But LAMP1, so this lysosomal granule membrane protein, which is a marker of activation, was again up, statistically so, in the Sacramento samples and somewhat also in the Davis samples in resting platelets indicative of activation. So Dr. Wilson's observations in the lung are closely paralleled by what we see by flow cytometry.
Okay, so I think now we're really going to kind of do it in tandem or trio, and we really would be happy to answer any questions that you might have. But I'm going to have Dr. Bynes start because those are critical questions about extraction.
So drag you back into the extraction and analyses world. So really quickly, run out of time. First of all this has been published in Atmospheric Environment. The citation is at the bottom there. And this is basically the first study to demonstrate an exhaustive chemical characterization of a single extract, the importance of directly characterizing the PM extract that you're going to use in toxicological studies rather than relying on parallel measurements, the relevance of directly measuring the extracted PM mass rather than using a pre- and post-filter weight difference technique. First study to show very substantial differences in the composition of different filter extraction techniques. And finally, the importance of standardizing filter extraction objectives to minimize study bias in toxicological studies. So with that, I'll pass on conclusions for the dose response to Kent.
Okay, so as we've learned in looking at these materials, it really does appear that the filter extraction method will critically influence your biological responses that you're going to see following administration of these materials to the respiratory tract. And again, our conclusion at this point is that really the spin-down method, the water extraction method, actually has provided the most important, the most potent effects in terms of inflammation and histopathology that we've recognized. But it is interesting, I didn't really emphasize it, but the fact that the PAHs in the multi-solvent extraction method does appear to be a bit more potent than in the extraction method, which we would kind of anticipate because of the presence of the preservation of the polyaromatic hydrocarbons.
So this kind of leads us to the paradox of this study, and this is very non-intuitive, so I want to take some time just to throw it out there. But what I showed was that the multi-solvent best conserves the original chemical composition of the PM as it was sampled from the atmosphere. I showed this through the mass closure analysis. And then what Dr. Pinkerton showed you was that the spin-down technique generally elicits the largest and most robust toxicological response. And it did this at half the dose, right? So what's the reason for these observations? There's several different possibilities. One is maybe the existence of toxicological matrix effects. And I borrowed this concept from the world of chemistry, where the presence of some constituents can interfere with the detection of others, either synergistically or antagonistically. So the spin down removed maybe the toxicologically inert compounds, which amplified the response to the active ones, whereas the multi-solvent, the objective was to remove everything, and so maybe the inert components diluted the response to the active ones, or maybe altering the physical composition of the PM alters the bioavailability, right? So this would be anything from particle size distribution. You could have agglomeration, or you could do component dissolution. You can rearrange the internal distribution of the chemical compounds, and that can affect bioavailability, as well as phase partitioning. Is it in the particulate form? Is it in its own separate immiscible little globule, or is it dissolved in the lung fluid? And then finally, obviously, the presence and the concentration of FGM, these are the fiberglass microfibers, can greatly affect toxicological response. The spin down did a much better job of removing these contaminant filters than the multi-solvent. Maybe that is the reason we're seeing these effects. We don't know. Further research is needed. And so the obvious question is which method is more important or more appropriate? And that depends on your study objective. Are you trying to conserve the original physical and chemical composition of your sample PM, or are you interested in producing the largest and most robust toxicological response? Again, more research is needed, but we need to standardize what our objectives are so that we can have comparative studies across the board. So with that, we'll go into time lag conclusions. Back to Kent.
Okay. So again, we did see significant shifts in our time response based on the particle type. And again, that really had to do with our dose response studies that we were doing, but also with this time delay. And again, it appears as though the urban PM does have a longer period of effects within the bronchoalveolar lavage, and as well as in our pathology that we're noting within the lung itself. I think there really are intriguing differences between airways and parenchyma, and it's something that we really need to understand. Because these particles that we're working with, this is pretty much PM 2.5, and it's certainly we would have a certain deposition within the airway tree, but also these are small enough that they can reach the parenchyma. And clearly, when we're looking at this, we really should be examining both things. But probably one of the things that is most intriguing to me is the eotaxin, because we're actually very much interested in this, in that this has a significant time lag following aspiration. Recommendations.
So we'll always end with recommendations for future work. And number one, reproducibility. These are very non-intuitive results, so the first step would try to be to reproduce these results. You could use different types of PM, you could change the extraction methods, or even the exposure models, but I think that would be first. And then secondly, better understand the effects of the extraction method on PM toxicity. Why such a difference between the spin down and the multi-solvent? Is it in fact some kind of toxicological matrix effect? Is something else going on? Is it an issue of bioavailability? Is it simply a bias of the filter media that we're using? And that leads to the next. Evaluate alternative filter media for PM toxicity testing. You want to minimize the toxicological artifacts, and maybe we want to switch away from a microfiber base to something different. And then always the long-standing questions. You want to quantify differential toxicity as a function of your filter media, as a function of your extraction technique, as a function of PM component, PM source, as well as toxicological endpoint. And finally, we should try to standardize the filter media and the extraction techniques that we use for toxicological studies, so that we don't introduce study bias from study to study. And with that, we conclude.
Great. So if there are questions, we'd be happy to address them. While you're thinking about that, I wanted to really mention something, and now we ought to go on first name basis. Keith, Kent, and Fern. So in essence, we spent a whole day at a PM conference for all 5 of the PM centers in the United States down in Los Angeles. This has been a few years ago, and we spent the entire, actually it was the entire afternoon arguing about extraction methods. And you would think that EPA has it all in hand, that they've been doing this for years, and they're still arguing about what is the best extraction method. Water, solvent, whatever it may be. But I just wanted to kind of add that, because I think that this research that's been sponsored by the Air Resources Board has really been the first time that we've ever done a head-to-head comparison of different extraction methods.
Yes, I have two questions for you. First one, when I think of Davis, South Davis, I think that's where you used, am I not correct? Was there a standardization used for the traffic flow on I-80 versus the traffic flow on 13th and H, I think you said it was?
Yeah, it's a good question. Actually, when I say South Davis, for those of you from South Davis, you think, wait a minute, there's a lot of people in South Davis. South Davis for us is Old Davis Road. So we go straight down from the campus.
That's better. That's
Okay,
a lot
and
better.
so when we're there, and actually if you think about the Delta breezes, we do not get the I-80 traffic because the wind would be blowing from south to north.
The second question that I have is that when you were introducing the material into the lungs, and you only used one lobe, if I recall correctly, am I correct?
What we did, we actually use every piece of lung possible. But when we do oral pharyngeal aspiration, we're at the level of the larynx, and so we're actually allowing the mouse to aspirate the suspension, and it will go into all lobes. At least we hope that that is the case, and so all lobes actually receive particles from the aspirate.
Okay. So why did you use mice and not rats?
Good
I mean,
question.
is that,
Yeah.
am I being pedantic?
No, because I actually love rats more than I love mice. So, and I've always been kind of
I'm just the opposite.
a rat guy. So,
Sorry.
but really what's happened, I mean, Keith has done an incredible job to provide us with lots and lots of material. Doesn't matter what the extraction method is, we get a lot of material to work with. So I cannot use the excuse that it was so precious that we had to use a smaller animal in order to look at the effects. But one thing that we do know is that when you use the aspiration technique, the oral pharyngeal aspiration technique, it works most effectively in the mouse and to a very variable degree in the rat. I don't know why. Maybe they just breathe a little bit differently, but a mouse gives you a very uniform, when you do the aspirate, it goes uniformly throughout the lung. Probably the only thing that would have been better is inhalation, but that was not possible.
Hi, Ken. This is probably a simplistic question, and you probably corrected for this, but obviously in a rural environment versus an urban environment, you're going to get a different concentration of particle number. So did you try to correct that when you did your aspiration? Because, you know, you would have a smaller amount in the urban area unless you did some sort of correction for the number. It could potentially be that the rural is more toxic per amount, you know.
Yeah, I think that's a really good point, because as we think of urban areas and emissions, that we're going to have a much finer particle and therefore potentially a greater number versus our urban area. If we're truly truly rural, it's going to be like agricultural crustal dust of a much larger size. And it is interesting because that could be a possibility, because as you see, our urban response of Sacramento is usually stronger than our rural Davis response, and that the time lag tends to be a little bit longer in an urban area compared to a rural area. And that might suggest that there is something about particle number. It's interesting though, as mentioned, that spin down method, the water extraction method, it's simple water extraction. And again, as Keith mentioned, when we do the multi-solvent, we know a precise dose. And we thought we were delivering the same dose when we used the spin down method, but we found out, oh, wait a minute, we lost a lot more particles than we did. And so we're actually giving a lower dose. But again, that even regardless, that still was showing that a stronger urban effect than a rural effect. And I don't know if Fern or Keith have some thoughts about rural versus urban PM, because we're spending a lot of time in agricultural areas now.
Right. I don't know. It's hard to standardize to the true concentrations in the atmosphere. Everything is done on an equal mass dose. But in reality, in true human exposure, somebody in a rural area is probably inhaling a larger particle at a lower concentration, and maybe only for particular times of the day when agricultural activity is going on, versus in an urban area where the particulate may be smaller at a much higher concentration and continuously being emitted. So it's hard to normalize out toxicological response to those variables. I'm not sure if anybody doing it right now. Everybody does an equal mass dose.
I think the other conundrum that is always present is the question of endotoxin, and you could make the argument in a rural environment that, especially because CHE is very close to the Center for Equine Health, that perhaps there's a contribution there as well. I don't think you could rule it out, but I don't think it would be very easy to be able to answer that directly either.
Well, I think one of the things that we're going to face, especially this summer, just like last summer, is that just the dust levels within the valley are likely to be very high. And because there are fields that are going unseeded, hopefully there is some sort of ground cover for that sort of thing, but there could be a lot of dust generated in that way. I would say that being a farmer, might be a little bit safer than being an urbanite in some regards. But then again, we're all going to experience the effects of wildfires if that becomes a true issue because of the continuing drought conditions here in the state of California. And I'm sure many of us lived through the summer of 2008 when we actually had concentrations of particulate in the air. Escalon is the one that I know the most about. It was 200 micrograms per cubic meter, which is clearly well above the concentration that we would want to have. So, any other questions?
Into the mic. I just missed it in the setup. You talked about sampling during both winter and summer, and in these studies, what was this, summer dust or winter dust?
We opted for winter because we figured the inversion would be the most optimal, and if we were going to try to capture emissions in an urban area, that may be vehicular, that we thought that would be the best. Is that we collected both. We've done other studies with the summer stuff, which has been really quite fascinating. But for this study here, because of our limited resources, we opted to stay with the winter because we felt that would be the most meaningful in terms of trying to understand dose response and lag time.
Thanks. Just one quick one. I missed in the dose responses, those were done at 1 day, is that right, after exposure?
Right.
Okay.
Yeah, and those were done 24 hours. What we did there, I don't think we really discussed it, but we did 10 micrograms, 50 micrograms, and 100 micrograms. And when we're doing studies on a nationwide basis, typically for a mouse, they'll be giving about 200 micrograms. Do you know, Rona? Is that about right? Well, I know you did rats, so yeah, it was different. So, but but the 10, 50, and 100 was good. And I know, again, sorry, Rona, but you were the one who would calculate these sorts of things. I don't know what a 50 microgram dose in a mouse would be, but it might be a couple of days of exposure to, but we don't really know. I guess it depends upon. Yeah, right, yeah. And it's, but anyway, that's those were the doses, but we opted for the 50. I mean, we knew we could use 100 and get all sorts of responses, but we really felt as though that might be, it's not an overload. It's clearly not an overload in the animals. They can handle that amount, but we really felt the 50 microgram level in the 50 microliter suspension would be best. And of course, with with Fern's work, she really was getting effects at, what is that, 27? That was your high dose, so 27 micrograms. And her low dose was 5 micrograms. So.
For urban areas, how much of these particulates are presumed to derive principally from the nearby interstate? How much are likely to be actual in the urban area rather than from the roadways, from the major highways?
That's Keith.
So we positioned the sampling site within a quarter mile of a major freeway interchange, particularly to select that emission source. There's sprawling residential areas that are going to contribute whatever residential sources you might have, such as cooking or residential heating or other things like that. But they will be at a lower percent contribution than all the vehicular traffic that's going on in that area. I would suspect, I don't have a number, but I would suspect that would be the largest contributing input source for the urban would be vehicular emissions. And it's going to be a mix of gasoline and diesel. So we didn't do any source attribution analyses or anything like that. All we did was a straightforward chemical analysis. But given the proximity to that major freeway interchange, I would suspect that a large fraction of it is vehicular emissions. And we kind of did that on purpose.
Okay, I'd like to thank all of you for coming today and especially thank our speakers for their interesting presentation. We don't seem to have gotten any online questions, so I think we'll wrap up for the day. And thank you all for coming.
You got off easy. Well, we're done tonight. We'll be able to do that.